Assalamualaikum everyone, I am Adder and today I am presenting you the implementation of half adder, half subtractor, full adder and full subtractor. Uh, we will implement this on Proteus and we will learn how to implement this circuit in digital logic design. So first of all we see what is adder and subtractor. Adder and subtractor are digital circuit that perform arithmetic function as name shows. Adder perform the addition of um, numbers and the subtractor perform the subtraction of number. It depends uh, how many bits we have to add and or we have to subtract. We can design according to our need. If I need 2-bit adder, 4-bit adder, 8-bit adder, 16-bit, 32-bit or 64-bit, we can design. So basically we will see how we design the adder or subtractor and how they work. So first we have half adder. Half adder will have two input A and B and two output. One is sum and the other one is carry. What is sum and what is carry? So we will see here in truth table that here we have a truth table of half adder. When we have number 0 and the second one is 0 0 0 0 plus 0 0, so sum is 0, carry is 0. When we have 0 1, sum is 1. When we have 1 0, sum is 1. 1 plus 0 is 1. But when we have 1 1, we have 1 0 mean 2. So here we have in sum we have 0 and the carry is 1. If we go in uh, more bits, we will have more uh, carry and therefore uh, carry is there for adder. Okay, so we understand what's the carry here. The carry is the number that comes in addition, um, in the result of addition, when we have a number like 1 1 and it gives us 1 0, that is 2 in decimal, so we will have a carry in here and the sum is 0. To basically to design this half adder, we see if we have an XOR function. An XOR function, we will A XOR B. We can see here that if we A XOR B, if we have 1 in any of our inputs, then sum is 1. So we will we can implement this function using the technique that we studied previously. We can make a boolean expression and simplify that, and we can make a k-map and that stuff. But this is you can see it's very simple and very small truth table and very small expression. So we can implement it using analyze and using our analysis. So A XOR B is sum. You can see when any of the input is 1, output is 1. But for carry, we have to make A and B. A and B, if both of the input is 1, so we will have sum 0, but we will have carry 1. That's the simple half adder circuit. What is full adder? The difference between full adder and half adder is that we have three input in full adder and two output, but in half adder we have two inputs and two output. So what is the third input here in full adder? The third input is C in. uh, we will have A, B and C in for our logic to implement that will help us to design a proper circuit that gives us sum and carry out. So in full adder we will have A, B and C in, and in output we have sum and carry out. So you can see a basic block diagram here: A, B and carry in, full adder, sum and carry out. And you can see that when a full adder logic is designed, you string 8 of them together. uh, 8 of them mean the logic that will become from A, B and C in a 8-bit uh, a different logic from 0 to 7. So or you can say a different combination. So we will string 8 of them together to create a byte wide adder and cascade the carry bit from one adder to the next. You see here that when we have carry input and 0 plus 0 in cascading, you can understand here from the full adder table that we have 0 plus 0 plus 0 is 0 and carry out will also be 0. In here 0 plus 0 plus 1, 0 plus 0 0, but 0 plus 1 is 1 sum, and similarly 0 plus 1 is 1 and 1 plus 0 is 0. You can check here that if we have 1 plus 0, that is 1, that is 1, but when we add it with this one, the output that comes out from 1 plus 0 is 1, and if we add that one with this one, we will get 1 0. Here is a 1 from here, 1 0, and the 1 is this one, so it will become 1 0 2. So we have carry out 1 and the sum is 0. Here 1 plus 1 is 1 0, so we will write 1 here in sum, and 0 plus 1 also 1, and we will write 1 here. So this is the complete uh, truth table for 3 input or 8 combination of a full adder. And the logic diagram, using gates, we have a full adder circuit like this one that can be implemented using boolean expression derived from this truth table using k-maps or different technique. We implement this circuit to perform our full adder circuit. In half adder and half subtractor and full subtractor, that is similar to full adder and full subtractor. The difference is here we have to subtract uh, two number. Okay, so uh, here we have input A and B, and if we subtract, you can see that the same goes to table 0 minus 0 0. The difference is here we have a borrow. You see when we difference and integer from the other one, we if the first integer is smaller in value and the second integer that is to be differenced from the first one is larger one, so we have to borrow a number from the integer next one integer. So the same logic goes here, that you see if we have 0 0, difference is 0, borrow is 0, 0 minus 1. Now 0 is smaller value, okay, and 1 is larger value, and if we have 0 minus 1, we have to borrow 1, okay, and this will become 1 0, that is 2, and when we differentiate this one from 1 0, we will get 1. As you know, 2 minus 1 is 1, and here 1 minus 0 1, and 0 1 minus 1 0 and 0. So you understand what's the purpose of borrow here is. If we have a smaller value here at the first input, then we have to borrow some integer to make differentiation possible. Okay, and the same logic goes to full subtractor. Just the difference is as similar we have in full adder, that there is a c in, carry in. So here we also have a, b and c in, and the same logic, difference and borrow. This is the circuit for half adder using and the one thing is, we can implement the logic of half subtractor. As you know, NAND and NOR gate is universal gate, and we can implement any logic through these NAND gate or NOR gates, and this is the circuit. It will perform the same function as this logic diagram, logic circuit half adder. And this is the circuit diagram of half subtractor. The only difference here is our not gate, and we have no not gate here, but we have a not gate here in borrow. And the we can implement this same function using only NOR NAND gates. And these are the logic circuits diagrams of full subtractor, and this one using NAND gates, and this is for full adder. Now I show you the screen of Proteus, where I implement these half adder, half subtractor, full adder, full subtractor. This is a circuit we implement using resistors, voltage, and for output we have LEDs, and these are the resistor, and push buttons for implementation of inputs A and B. And let me show you the simulation, that will it follow our truth table or not. Okay, so we have half adder and half subtractor, and these are the circuits using NAND gates. I run the simulation. You see we have 0 0, 0 plus 0 is 0 0. Okay, so no carry, no sum, and similarly 0 and 0. If I make it, this is A and this is B, and if I make it 1 and this is 0, 1 plus 0, so we see what's the answer. And similarly here we have 1 and here is 0. So when we add 1 plus 0 and we add 1 plus 0, we have 1 at sum. And if we add 1 plus 1, what we have, we must have a carry. You see here that in half adder, when we have 1 1, we have 0 1. So our logic is to be followed. And similarly in half subtractor, when we uh, have input 0 0, the output is 0, difference and borrow. But if I change it to 0 and 1, 0 A0 B1. Okay, A0 B1. So you can see when we subtract 0 from 1, we will have to borrow some number, uh, and then when we borrow the number, 0 will become 1 0, and when we subtract 1 from 1 0, it will become 1, and borrow will also grow. And the same logic is for choosing on NAND gates. Next thing, I shall show you the full adder. Here is the circuit of full adder, and this one is using NAND gates. This is for full subtractor, and this one is using NAND gate. And here we have A, B, and C in, and similarly here we have A, B, and C in, and in subtractor here we have A, B, and B in, borrow in, and A, B, and borrow in, and difference and borrow out. And for adder we have sum and C out. So I will run the simulation. You see, when we have 1 1 1 A, B, C, and let me show you the truth table, that what we have when we have 1 1. When we have 1 1 1 in full adder, 1 plus 1 is 1 0. So we have output of 1 for sum, and when we add that 0, remaining 0, with this one, so it will become 1. So you see, and you see that in here I have 1 1 1, and this is 1 or 1. Okay, and similarly for the AND gate, for full subtractor we will use something other value. We check this one, 0 1 1. A, B, A is 0, B is 1, and borrow in is 1. A is 1, A is 0, B is 1, B in is 1, 0 1 1. So you see that difference is 0 and B out is 1. Difference is 0 and B out is 1. Okay, that all for today. Thank you for watching, and Allah Hafiz.